Hi everyone, in this video we're gonna prove that during elastic clearance the magnitude of the relative velocity between the two objects stayed the same before and after clearance, which is mentioned in part 2 of this series of video. And note, what is elastic clearance? So during elastic clearance, both momentum and kinetic energy is conserved, and that means there's no loss of kinetic energy to heat energy or sound energy, which normally would happen in inelastic clearance. And of course, the momentum is always conserved like any other clearance. Alright, so let's get to it. So first of all, let's assume a situation where you have a ball with mass m1 and a velocity of v going to the right. It's gonna collide with m2, which is initially at rest. So this is before their clearance, and after clearance, m1's velocity changed to v1 and m2's velocity changed to v2. By the way, here, even though I'm drawing v1 to the right, but it can be to the left. We're working with velocity here, which is a vector, has directions. So now I'm gonna calculate their relative velocity before clearance. So let's say v21, which is the velocity of v2 minus v1, and v2 is 0, v1 is, if I define this to be my positive direction, v1 is v, so 0 minus v is negative v, and the magnitude of their relative velocity is just a v. Okay, and after clearance, again, v relative is v21 equals to v2 minus v1, and the absolute value, which is the magnitude of their relative velocity, is absolute value v2 minus v1. Okay. So this is the magnitude of the relative velocity before, and this is the magnitude of the relative velocity after. And I'm trying to prove they are the same, right? That's our goal. So our goal is to prove v equals to absolute value v2 minus v1. So this is our goal of this video. Okay. So I'm gonna start to build my equations with conservation of momentum and conservation of kinetic energy. I can build two equations. Okay. So first of all, conservation of momentum, initial momentum m1v equals to final momentum m1v1 plus m2v2. This is my first equation. Second equation, the kinetic energy is also conserved, right, during this elastic clearance. Kinetic energy before is a half m1 v squared equals to kinetic energy after a half m1 v1 squared plus a half m2 v2 squared. So this is my second equation. Alright, so you can see in this equation I have v, v1, and v2. m1, m2, you can treat them as constant, just the mass. But in fact, I'm also going to treat v as constant. Okay? The reason is, this is my goal, right? I'm trying to prove v equals to absolute value v2 minus v1. If I can represent v2 and v1 with v, and then I plug them into this expression v2 minus v1 absolute value. Technically, I should be able to get v, right? So this is my goal. With those two equations, I'm gonna try to represent v2 and v1 with v, and then I'm gonna plug them into this equation. Hopefully they will give me v. Okay? And I can actually do that because if I treat v as my constant as well, I have two equations here, and I have two variables, v1 and v2. Right, two equations, two variables. I can surely solve these systems of equations. Alright guys, yeah, I'm back. I have to pause the video because the garbage truck came and then the dog started to bark. Alright, so I have two equations, I have two variables, v1, v2, and I can solve it. Alright, so first of all, what I'm going to do is I'm going to rewrite first equation and get v2 by itself. Basically, I'm going to have to move m1 v1 to the left first. So I'm going to minus m1 v1 from both sides. And on the right, I have m2 v2. And then I'm just going to divide m2. So now v2 is equal to m1v minus m1 v1 divided by m2. And then I will plug v2 in here. So I will have a half m1 b squared equals to a half m1 b1 squared equals to a half m2 b2 squared, m1b minus m1b1 over m2 squared. Okay. As you can see, this is basically a quadratic equation with the variable being v1, and I can surely solve it like I solve any quadratic equation. The reason you may find the derivation in this video a bit complicated is just because we're using variables instead of numbers. Imagine if m1, m2, v are all numbers, we can really easily find out the solution of the equation. But since we're working with variables, it takes more work, but we'll get there. So now with this quadratic equation of v1, I can surely solve for v1 using v, m1, m2 to represent v1. So let's tidy things up a bit. So first of all, we can get rid of all the half because it is in all the terms. And from there, let's write down what we have left. m1 v1 squared plus m2 times m1 v minus m1 v1 squared over m2 squared. And you can see m2 here can cancel out one of the m2 in the denominator, so I have just the m2 left in the denominator. And from, okay, let me just write it down. Plus m1v minus m1v1 squared over m2. And then I'm going to multiply m2 on both sides. So I have m1, m2 v squared equals to m1, m2 v1 squared plus m1 v minus m1 v1 squared. Here we go again. Let me pause the video. Alright, we're back again. Sorry, but the garbage truck is not supposed to come at this time. Alright, let's continue. And then we can actually cancel out M1. Can you see that? It's in here. It's in here, and there's a M1 square here. Let me write one more step so you can see it better. So in the bracket, I'm gonna take M1 out, then I have V minus V1 left, right? Then I square it. I have M1 squared times V minus V1 squared. Okay. So I can cancel out M1, one of the M1 here. And I have a M2V squared equals to M2V1 squared plus M1 V minus V1 squared. And from there, I'm gonna extend V1 squared plus, I'm gonna expand this expression, so it becomes V squared plus V1 squared minus 2V1. Continue. M2V squared equals to M2V1 squared plus, multiply out the bracket, M1V squared plus M1V1 squared minus 2M1V times V1. Alright, since V1 is my variable in this quadratic equation, I'm gonna rewrite everything, rearrange everything with in the decreasing order of the exponents of V1. So basically, I'm gonna minus M2V on both sides first, and minus M2V squared, and then I will have on the right, on the left is 0, on the right it becomes M1 plus M2 V1 squared. So I'm combining those two like terms, so write V1 squared first, and then I have a V1 here, so minus 2M1 VV1, and I have plus M1V squared, M1V squared minus M2V squared. Okay. So this is like quadratic equation with, this is like x squared x, this is like the constant term. Okay, so this is in the decreasing order of the exponent of x, basically. I like to have 0 on the right. Alright, so now we need to factor this equation, but in fact you can use quadratic formula as well, and to solve for V1. You can already tell we can solve this equation because it's already in quadratic form. So it just comes down to if we should factor it or use quadratic equation. I prefer to factor. I kind of know it's factorable, even though it doesn't look factorable, because I know my final answer has to be quite simple, because eventually V1 minus V2 or V2 minus V1 has to give me V, right? Has to give me V. So I'm sure I can represent V1, V2 with V fairly easily without having this really ugly with square root stuff like that in the expression. So I'm confident that I can factor it. And so how do I factor it? I'm going to use what we call crisscross method. Let me briefly go over what is crisscross method. Let's say you have an equation like this, quadratic equation, and if you want to factor it, you find two numbers that multiply to a, which is the coefficient of x squared. So 3, 1. 3 times 1 is 3. And you find two numbers, basically two factors of 6 that multiply to 6. Let's say 2 and 3. Then you write them in the same column, 2 and 3. And then you do crisscross. What that means is crisscross 3 times 3, 1 times 2. Then you add your answer. See if you can get the number in the middle. And in this case, yes, 3 times 3 is 9, 1 times 2 is 2, 9 plus 2 is 11. Right on. So the factor result is 3x, put the x here. Then this is going to be one of the factor. This is going to be the other factor. So the result is 3x plus 2 times x plus 3. Okay, and you may ask, why did it work out the first time? And of course not. You may first came up with, for example, you put 3 here, 2 here. Then when you do crisscross, you get 9 actually. It doesn't equal to 11. So you have to switch things around and to make it work. Okay, so I'm just briefly showing you the idea of crisscross. If you want to learn more about it, you can Google or YouTube, or maybe I'll make another video about it. So this is the method we're going to use. Okay, and basically the idea is we find two numbers multiplied to a, which is m1 plus m2. We don't have many choice, just m1 plus m2 and 1. Right, so one of the factors is m1 plus m2 itself, the other one is 1. And our constant term is a little bit more complicated, right? But if you look at, eventually you need to get the middle term, which is negative 2m1v. You cannot have v squared in here, right? When you have the factor in here, you cannot have v squared because eventually your answer only has v. So apparently you're going to break it up into m1v. So you can factor it first. So it becomes, just take one of the v out. You have m1v minus m2v. Okay. So, and I'm just going to give you the answer actually. So eventually it becomes, so let me give you the answer, m1 plus m2. I did try this a couple of times before I get it. So eventually this is negative m1v minus m2v. And then this is negative v. Okay. And then when you do crisscross, it works out to be negative 2m1v. Okay. So first of all, let's check this term multiplies this term does give us back that, right? Because negative cancels out. You have v times m1v minus m2v. And when we do crisscross, let's see what do we get. Crisscross, you have m1 plus m2 times negative v, and plus 1 times negative m1v minus m2v. Okay, and this gives you negative m1v minus m2v, and this gives you positive because, oh sorry, not positive, this is 1, right? So it's basically, you don't need to look at it. And then you have minus m1v minus m2v, right? I'm just copying down this term with the negative in front, so this becomes minus. And then you can subtract out the bracket, so you need to change the sign of the second term, becomes m2v. And then negative m2v, positive m2v cancels out. You have negative 2m1v left, which is your middle term over here, right? Which is this term. This gives you the middle term. So this is the correct crisscross. And that also means this gives us the answer. So m1 plus m2 would be one of the coefficient of v1, and minus we have here m1v minus m2v. The other factor is v1 minus v equal to 0. Okay, so this is just how you write your result after you get your crisscross. Okay, so basically you put v1 here and v1 here, and then you add this this term, then it becomes the first factor, then this becomes the second factor. All right, so we have two solutions, either this one equals to 0 or this equals to 0, but v1 minus v cannot be equal to 0 because if you look at the situation here, v1 is gonna be either smaller than v, or it's gonna be going to the other direction. Right, so v1 cannot be exactly the same as v. The v is gonna change. Basically, this velocity of m1 is gonna change. So v cannot be equal to v1. So their difference cannot be 0. So that left us m1 plus m2 v1 minus m1v minus m2v equals to 0. So the first factor has to be 0. And there we go. We get v1 by itself, then we can represent v1 with v. So v1 equals to, you add the entire bracket to the other side, m1v minus m2v, and you divide m1 plus m2 on both sides. Cancels out. Finally, this is how we represent v1 with v. Okay. All right, now we're gonna plug it back into the very first equation here. Let's see, m1. Let's plug it back into the equation here. Since we represented v1 with v, and when we plug it in, we have v2 and v in the same equation, then we can represent v2 with v. Okay. All right, so let's do that. When we plug it in, we have m1v equals to m1 times m1v minus m2v over m1 plus m2. So this used to be just v1, right? I'm just replacing v1 with this expression I just got, and plus m2v2. This is the original conservation of momentum equation. Now I have v and v2, v and v2. I can represent v2 with v. And apparently I need to get v2 by itself first. So I'm going to minus the entire expression here to the left. m1v minus m2v over m1 plus m2 equals to m2v2. I just need to tidy it up a little bit. So I'm gonna get the common denominator first. So I multiply m1v by m1 plus m2. So I have m1 plus m2 on the bottom as well. And so I'm getting this term and this term with common denominator, m1 plus m2. And this term becomes minus m1 times m1v minus m2v divided by m1 plus m2. I just moved m1 to the top, equals to m2v2. Continue. So they are a common denominator, so I can write the expression on the top together. So that becomes m1v plus m1 plus m2 minus m1 times m1v minus m2v bracket equals to m2v2. Alright, multiply out the bracket becomes m1 squared v plus m1 m2v minus m1 squared v plus m1 m2v over m1 plus m2 equals to m2v2. Okay, so again here when I multiply out the bracket, be careful of the negative sign. This will turn this bracket, this negative will turn this negative into positive, because two negative make a positive. That's why I have a positive here, and this is just negative m1 squared v. Okay, all right, now you can see this cancels out, so I have, and those are the exactly same terms. So it's 2m1 m2v equals to m1 plus m2 equals to m2v2. Well, looks good, right? Because now you can cancel out m2. Now you get v2 by itself, and on the right you have 2m1v over m1 plus m2. Good. So we have v2 represented by v, and here we have v1 represented by v. Now we can plug both the equation into the original equation here, v2 minus v1, and then absolute value, and let's see if we can just simplify everything to just v. All right, looks magical, right? The expression becomes more and more simple as we go, actually, even though it started out to be ugly, but eventually that turns out to be neat. That's one of the beauty of math. It simplifies the complex situation into a much easier situation. All right, so v2 minus v1 is equal to 2m1v over m1 plus m2 minus m1 minus m2 v over m1 plus m2. Again, this is v2 represented by v, and this is v1 represented by v, which we got over here. Okay, all right, now they already have the common denominator, so I'm just gonna work with the expression in the numerator, minus m1 minus m2v, and then equals to 2m1v minus m1v plus m2v. Again, you have to change the sign of the second term over m1 plus m2. Oh, it looks good, because 2m1v minus m1v is just m1v plus m2v over m1 plus m2, and you can take out the common factor v, so that becomes m1 plus m2 in bracket divided by m1 plus m2, and that cancels out. You have a really nice result in the end, which is v, and if you put absolute value around them, there you go. That's your proof. v2 minus v1 absolute value equals to v, which is, remind you, our ultimate goal here, right? This is our goal here. And that tells you the magnitude of the relative velocity is the same before and after clearing, right? Because this is the magnitude of relative velocity before, and this is the magnitude of the relative velocity after. They are the same. And they can be any arbitrary values because we're using just letters, right? We're not using specific numbers. So this works for any situations. And that is your proof. For an important conclusion we used in part 2 of the video to show you how the stacked ball drop works. And even though it does appear a bit ugly, the derivation, there's a lot of like letters and rearrangement of expressions, solving quadratic equations. But if you think about it, everything in here is grade 10 math, pre-calculus 11 math, right? There's really no fancy math there. It's just like I said, we're working with letters, we're working with not with numbers, so it looks a bit more complicated. If they're all numbers, like M1, M2, V are all numbers, it's a lot easier to solve. But we want to come up with a generic proof. That's why we're using letters instead of numbers. Alright, hope you enjoyed the video, and if you haven't checked out part 1, part 2, please go ahead. I'm gonna put a link below and check them out as well.